Greetings from MWN.com. Dr. M. Wilson, formerly Vice Principal and Head of Department of Commerce, Nagarcoil is delighted in presenting this session. Thank you. Please subscribe the channel MWN.com. Chapter 13. Probability. The probability theory was developed during 17th century to solve the problems in gambling. The famous mathematicians in their locality were approached by gamblers for their gambling problems. The mathematicians gave some idea which was related to the probability theory. The origin of probability is that a French mathematician Blaise Pascal first solved the question raised by a French nobleman Antoine Gambald, with regard to gambling. Antoine Gambald is known as Chevalier de Mere. Pascal discussed the problem raised by de Mere with other French mathematician Pierre de Fermat. This laid the foundation for the theory of probability. This theory got a gradual development during the 18th century. The other contributors for the development of probability theory are de Moivre, 1718, James Bernoulli, 1713, and Bayes, 1768. The theory was further developed by the mathematicians like R.A. Fisher and Pearson, J. Neyman. Meaning of probability. Probability is the prediction of the degree of possibility of occurrence or non-occurrence of an event. It is initially applied in games of chance, like tossing of coin, throwing of dice and playing cards. Now the theory is widely used in solving various managerial problems of companies, government and social organizations. People are interested in predicting the occurrence or non-occurrence of an event in future in their day-to-day life. It is difficult for them to say what will happen in future. Hence, they require some theory to determine the chance of happening or not happening an event in future. The theory required for the prediction is called probability theory. Approaches to probability. There are four important schools of thought on probability. They are 1. Classical or a priori approach. 2. Relative frequency or empirical approach. 3. Axiomatic approach. 4. Subjective approach. Classical approach to probability. It is the oldest method of measuring probability. This method is most suitable for gambling situation, since the method had its origin in gambling games. In classical approach, the probability of an event is the ratio of number of favorable outcomes of an event to the number of possible outcomes. The character of possible outcomes is that each event is likely to occur. The probability of occurrence of an event A is measured as P(A) equals A by A plus B, where A equals number of outcomes favorable to the occurrence of A. A plus B equals total number of possible outcomes. The probability of non-occurrence of A can be denoted as QA, and it can be measured as QA equals Q by A plus B, where B equals number of outcomes not favorable to the occurrence of A. For example, in the throw of a die the probability of occurrence of number 5 is P5 equals 1/6. Since in the die there is 1/4 and the total outcome is 6. Relative frequency approach to probability. The British statisticians formulated the relative frequency approach to probability during 1800s. This approach is useful in solving problems which could not be solved through classical approach. This approach stated that the valid procedure for determining the probability is through repetitive experiments. For example, if a coin is tossed once, then the probability of getting head is 1/2, i.e., 0.5. If the coin is tossed repeatedly, say, for 10 times, one can get 3 heads and 7 tails. Hence, the probability of getting head is 3/10 equals 0.3. When the number of repetition is increased to 100 times, one may get head for 42 times. Now the probability of getting head is 42/100 equals 0.42. When the repetition is further increased to 500 times, it is possible to get heads for 240 times. Therefore, the probability of getting head is 240/500 equals 0.48. It is very close to 0.5. Hence, in practice the probability can be measured accurately through repetitive experiments. It can be represented here. Classical approach to probability. It is the oldest method of measuring probability. This method is most suitable for gambling situation, since the method had its origin in gambling games. In classical approach, the probability of an event is the ratio of number of favorable outcomes of an event to the number of possible outcomes. The character of possible outcomes is that each event is likely to occur. The probability of occurrence of an event A is measured as P(A) equals A by A plus B, where A equals number of outcomes favorable to the occurrence of A. A plus B equals total number of possible outcomes. The probability of non-occurrence of A can be denoted as QA, and it can be measured as QA equals Q by A plus B, where B equals number of outcomes not favorable to the occurrence of A. For example, in the throw of a die, the probability of occurrence of number 5 is P5 equals 1/6. Since in the die there is 1/4 and the total outcome is 6. Axiomatic approach to probability. A.N. Kolmogorov, a Russian mathematician, developed the axiomatic approach to probability. According to this approach, the probability of occurrence of either of two events is the total of the probability of occurrence of each event individually. This approach is applied when the events are mutually exclusive disjoint. For example, if X and U are two mutually exclusive events, then the probability of occurrence of either X or U is P(x)(y) equals P(x) plus P(y). 4. Subjective approach to probability. Frank Ramsey formulated the subjective approach to probability during 1926. This approach is otherwise called as personalistic approach to probability. According to subjective approach, probability may be defined on the basis of the personal judgment of an individual. The personal judgment of an individual depends on evidence and the experience of the individual. For example, an individual may judge the probability of arrival of a train at 9:30 a.m. as 0.7, on the basis of the punctuality in the arrival of the train at 8:30 a.m. in previous days. An individual may judge the probability of his getting above 75 marks in an examination as 90%, i.e., 0.9, on the basis of his hard work and the nature of the question papers. Hence, an individual assign probability of occurrence of an event from 0 to 1. If one is very sure that an event will occur, then he may determine the probability is very close to no. 1. The main limitation of this approach is that the value of probability differs from one individual to other. Fundamental concepts of probability. The important concepts of probability are 1. Random experiment. 2. Sample space. 3. Event. 4. Equally likely events. 5. Mutually exclusive events. 6. Exhaustive events. 7. Independent events. 8. Dependent events. 9. Complementary events. 1. Random experiment. Random experiment is an experiment and the result of it depends on chance, e.g., tossing of coins, throwing of dice, etc. In a random experiment, the possible outcomes are known well in advance. The occurrence of an event depends upon mere chance. The experiment conducted to obtain an outcome is called random experiment, e.g., in the tossing of coin the outcome are head and tail. In the throw of die the outcome are 1, 2, 3, 4, 5, 6. In a random experiment any one of this outcome may occur. Sample space. Sample space means the collection of all possible outcomes. It may also be termed as set of all possible outcomes. The sample spaces for tossing a coin are head and tail. The sample spaces of throwing a die are 1, 2, 3, 4, 5 and 6. Each possible outcome in the sample space is called sample point or element. 3. Event. Any element of the sample space is called event. It is also called a sample point. Event may be simple event and complex event. If the event contains one element it is called simple event. If the event is defined by more than one sample point element it is called compound or complex event. 4. Equally likely events. If all the elements of the sample space got equal chance of occurrence or being selected it is called equally likely events. In the tossing of a coin the head and tail are equally likely events. In the throwing of a die 1, 2, 3, 4, 5, 6 are equally likely events. 5. Mutually exclusive events. Mutually exclusive events mean those event or events the occurrence of which prevents the possibility of the occurrence of other. It means if one event occurs the other event will not occur. When a coin is tossed either head or tail may occur. Hence, head and tail are mutually exclusive events. Exhaustive events. Exhaustive events mean that at least one of the events should necessarily occur. In the throw of a die there exist 6 exhaustive events. 7. Independent events. Independent events are those events, the occurrence of which does not affect the occurrence of other events. Independent events have no influence over the occurrence of other events. The occurrence of head in a toss of coin won't affect the occurrence of head in the second and subsequent tosses. 8. Dependent events. Dependent events are those events the occurrence of which affects the occurrence of other events. For example, the probability of drawing a queen from a pack of 52 cards is 4/52, i.e., 1/13. In the first draw if the incident happened, and the card is not replaced, the probability of getting another queen card is 3/51. If the queen card is not replaced and then the probability of getting a king card is 4/51. 9. Complementary events. The non-occurrence events are called complementary events. In the throw of a die, if we expect number 5 should occur, then the other events i.e., number 1, 2, 3, 4, and 6 are complementary events. Set theory. Set theory is applied in the modern approach to the probability theory. The important concepts of set theory, applied in the probability theory, are stated below. Set. Set means the collection of well-defined and specified elements or objects, e.g., the books in a library, the students in a class, the employees in a company, etc. Universal set. The set consisting of all the elements under consideration is called universal set. For example, if A is a set and U is the universal set, then every element in A must be in U. Null set. The null set or empty set is a set having no element. Subset. When every element of a set is also elements for another set, the first set is called the subset of the second set. For example, set A equals 1, 3, 9, and set B equals 1, 2, 3, 4, 5, 7, 9, 10, 20 are the two sets. Here, A is called the subset of B since every element of A is also the elements of B. It can be denoted as AIV. Equal sets. Two sets are called equal sets when the elements of both the sets are the same. For example, A and V are equal sets. When A equals 3, 5, 7, 9, and V equals 3, 5, 7, 9. It can be represented as AIB and BIA. Functions of set. 1. Intersection of set. When two sets are having few common elements, then it is called intersection of sets. In sets, A equals 4, 6, 8, 10, and V equals 1, 2, 5, 6, 10, the elements 6 and 10 are common, which are called intersection of sets A and V, i.e., ACV equals 6, 10. It can be written as ACV equals X, XA and HIV. Intersection of sets can be diagrammatically represented as follows. Disjoint sets. When two sets are not having common elements, then the two sets are called disjoint sets. Example, A equals 1, 5, 7, 9, and B equals 2, 3, 6, 10, are two sets. These sets do not have common elements. Hence, A and V are called disjoint sets. It can be represented as ACV equals F, where F is a null set. Disjoint sets are represented in the following diagram. Union of sets. The set of elements belonging to two sets is called union of sets. For example, A equals L, 2, 3, 4, 5, and B equals 2, 4, 6, 8, 10. The elements belonging to A and V are 1, 2, 3, 4, 5, 6, and 10. They are called union of sets. It can be written as AEV equals 11, 2, 3, 4, 5, 6, 8, 10. Hence, AEV equals XXIA or IB. Complement of a set. Set of all elements to the universe except the elements of a particular set is called complement of a set. If U equals 1, 2, 3, 4, 5, 6, 7, 8, and A equals 2, 3, 5, then the set of the elements 1, 4, 6, 7, 8 is called complement set. It can be written as A equals 1, 4, 6, 7, 8. Hence, A equals XXIU and XIA. Complement of a set is diagrammatically represented as follows. Difference of two sets. The set of elements of a set except the intersection elements of the set is called the difference between one set with another set. If A equals 3, 4, 5, 6, 8, and V equals 4, 5, 6, AV equals 3, 8. It can be represented as A V equals X, XA and XI diaresis V. Difference of two sets is shown in the following diagram. Permutations and combinations. Permutations and combinations are the important counting techniques for the calculation of probability of an event. Permutation. Permutation means the arrangement of number of objects in a definite order. The number of permutation depends upon the total number of objects and the number of objects taken at a time for arrangement. The formula for calculating permutation is NPR equals n factorial by n minus r factorial. Exclamation mark. Equals factorial. N equals total number of objects. R equals number of objects at a time. NPN equals n factorial. Illustration. 1. Find out the number of ways 5 books in a library can be arranged by taking all books at a time. Solution. NPN equals n. Equals 5. Equals 1x 2x 3x 4x 5 equals 120 times. Hence, 120 times the 5 books can be arranged. Illustration. 2A company received 10 applications for 4 posts. Find out, in how many ways 4 people can be selected for the 9 applications. Solution. The number of ways 4 people can be selected from the 9 applications is calculated as NPR equals n factorial by n minus r factorial. 10p4 equals 10x 9x 8x 7 equals 5040. This can be written as 10x 9x 8x 7 straight away. When r value is 4 and n value is 10, then 4 numbers as that of r should be used in the multiplication by taking an ascending order, that is 10x 9x 8x 7. Combinations. Combination is a technique of selection of objects without considering their order. The formula for calculating combination is NCR equals n factorial by n minus r factorial into r factorial. NCn equals 1. NC1 equals n. N equals number of objects. R equals number of objects taken at a time. Exclamation mark. Equals factorial. Illustration 3. A basket contains 10 oranges. In how many ways 3 oranges can be selected from the basket? Solution. NCR equals n factorial by n minus r factorial into r factorial. When r value is 3 and n value is 10, then 3 number as that of r should be used in the numerator and denominator. That is 10x 9x 8 in the numerator and 1x 2x 3 in the denominator. Otherwise, multiplications of 1 to 10 in the numerator and 1 to 7 and 1, 2 and 3 of multiplications in the denominator. 7 here means 10 minus 3. Illustration 5. Find out the probability of getting a 3 heads, B, at least 2 heads, and C, at least 1 head, when 5 coins are tossed at a time. Solution. A probability of getting 3 heads. P3 equals 5C3 cubed Q square equals 5 factorial by 3 factorial into 2 factorial into 1 by 2 raised 3 into 1 by 2 raised 3 1 by 2 raised 3. The easy method of calculation is when 5p3 means 5 factorial in the numerator and 3 factorial and the balance in 5 after 3 is 2 and these 2 are in denominator. Then these should be multiplied with 1 by 2 raised 5 since the base in 2 multiplications are same, that is 1 by 2. B. Probability of getting at least 2 heads, P equal and greater than 2. Hence P2 is included. Hence P equal or greater than 2 equals P2 plus P3 plus P4 plus P5. Hence in all cases 1 by 2 raised 5 since the base in 2 multiplications, that is for P and Q, are same, that is 1 by 2. In the calculations of factorials, smallest of that factorial among the 2 in the denominator should be taken into consideration. Suppose it is 2 and then the other one will be 3 in the case of 5 samples. Then in the numerator multiplication will be like 3 into 4 and in the denominator, multiplication will be like 1 into 2. The calculations can be done like that in all illustrations. If 5C2 means it will follow with P raised 2 and Q raised 3. If 5C3 means it will follow with P raised 3 and Q raised 2. P equal or greater than 2 equals P2 plus P3 plus P4 plus P5 is calculated as 0.813. It may otherwise be calculated as P less than or equal to 2 equals 1 minus P raised 0 plus P1. This is because out of the 6 values of P for 5 samples, 4 values should be added for P2 equal or greater than 2. Hence other 2 values like P0 and P1 are there. Total of all outcomes should is 1. Hence 1 minus the sum of the P0 and P1 would be the expected result. Probability of getting at least 1 head. This is just like the previous one. That is, P equals or greater than 1 1 equals P1 plus P2 plus P3 plus P4 plus P5. Explanation is just like that for the previous question. Illustration 6. The average percentage of pass in a test paper is 70. Find out the probability that out of a group of 7 students at least 4 passed in the examination. Solution. Percentage of pass in the examination P equals 70% equals 0.7. Hence, Q equals 1 P equals 1 0.7 equals 0.3. The probability of passing of 54 or more students, at least 4 students. At least 4 means includes P4. In the same way of previous calculation should be done. But in this problem the base for P and Q are different, that is 0.7 and 0.3, hence the values of it should be calculated separately. P greater or equals 4 equals P4 plus P5 plus P6 plus P7. Equals 0.21 plus 0.315 plus 0.245 plus 0.082 equals 0.852. Illustration 7. The probability of success in an examination of students in a village is 0.2. What is the probability that out of 6 students, I, none, E, 1, E, 2 and IV, at least 1 will be succeed in the examination? Solution. N equals 6, P equals 0.2, Q equals 1 to 0.2 equals 0.8. I. Probability of none success equals 1 by 0.082 equals 0.262. Please note that power of 0 to any number equals 1. Hence 0.2 raised to 0 equals 1. E. Probability of 1 success equals 6c1, 0.2 raise 1 into 0.8 raise 5 equals 6 by 0.066 equals 0.396. E. Probability of 2 success equals 15 by 0.016 equals 0.24. IV. Probability of at least 1 success equals 1. Probability of no success equals 1 to 0.262 equals 0.738. Illustration 8. 12 coins are tossed at a time. Find out the probability in a single tossing for the following outcomes. I. Less than 4 heads. E. 9 or more heads. E. At least 7 heads. IV. No heads. V. At least 1 head. Solution. Probability of getting head P equals 0.5. Probability of getting tail Q equals 0.5. I. Probability of getting less than 4 heads means P4 is excluded. P less than 4 equals P0 plus P1 plus P2 plus P3 equals 1 by 0.00024 plus 12 by 0.00024 plus 66 by 0.00024 plus 220 by 0.00024 equals 0.00024 plus 0.0029 plus 0.017 plus 0.053 equals 0.073. Probability of getting 9 or more heads mean P9 included. P greater than or equals 9 equals P9 plus P10 plus P11 plus P12 equals 0.53 plus 0.017 plus 0.0024 equals 0.073. E. Probability of getting at least 7 heads mean P7 included. P greater than or equals 7 equals P7 plus P8 plus P greater than or equals 9. This is because P greater than or equals 9 is already calculated. Equals 792 by 0.00024 plus 495 by 0.00024 plus 0.073 equals 0.19 plus 0.119 plus 0.073 equals 0.382. IV. Probability of getting no heads equals 1 2 CO 0.5 raised 12 equals 1x 0.00024 equals 0.00024. V. Probability of getting at least 1 head means no head should be recorded. Hence P0 is excluded from the total probability of 1 equals 1. P0 equals 1 0.0024 equals 0.9998. Illustration 9. A basket contains 300 apples. Out of the total apples 120 are defective. When 7 apples are selected at random, determine the probability that I. At least 1 is defective. E. At the most 5 are defective. E. All 8 are defective and IV. All 8 are good. V. All 4 are defectives. Solution. Probability of defective P equals 120 by 300 equals 0.4. Probability of good Q equals 1 minus 0.4 equals 0.6. I. Probability of at least 1 defective is P1 plus P2 plus P3 plus P7, or 1Q0 equals 1 to 7 CO 0.60 0.47 equals 0.998. Method of calculation is already explained in the previous illustration. E. Probability of at the most 5 defective, also P5 included. If it is less than 5 means P5 should not be included. P less than or equals 5 equals P0 plus P1 plus P2 plus P3 plus P4 plus P5 equals 1 P6 plus P7 equals 1 0.0168 plus 0.0016 equals 1 0.0184 equals 0.982. If unexpected events are less than, it may be calculated like this. That is 1 P6 plus P7. E. Probability of all 7 are defective is P7 equals 0.002. IV. Probability of all 7 good is P0 equals 0.028. V. Probability of 4 defectives is P4 equals 35 0.0256 0.216 equals 0.19. Here R is considered as defective. Theorems of probability. The theorems of probability are otherwise called as rules of probability or laws of probability. There are 2 important theorems of probability. They are 1. Addition theorem and 2. Multiplication theorem. 1. Addition theorem of probability. It contained two theorems, namely I. Theorem of total probability and E. Generalized theorem on total probability. I. Theorem of total probability. When events are mutually exclusive, this theorem should be applied. If two events A and B are mutually exclusive, then the probability of occurrence of either of the events A or B is equal to the sum of the probabilities of A and B. That is P A or B equals P A plus P B. If A1, A2, A3, A4 and are mutually exclusive events, then the probability of occurrence of either of these events is the sum of the probabilities of A1, A2, A3 and, i.e., P A1 union A2 union A3. Union and equals P A1 plus P A2 plus P A3. P an. Illustration 10. An urn contains 5 white, 3 red and 4 black balls. Find out the probability of getting a white or black ball in a single draw. Solution. Probability of getting a white ball equals 5/12. Probability of getting a red ball equals 3/12. Probability of getting either a white or red ball equals 5/12 plus 3/12 equals 8/12 equals 2/3. 2. Generalized theorem on total probability. This theorem should be applied when the events are not mutually exclusive. If A and B are two events which are not mutually exclusive, then the probability of occurrence of either A or B is P A or B equals P A plus P B P A and B. If A, B and C are three events which are not mutually exclusive, then P A union B union union C equals P A plus P B plus P C P A C B P A C C P B intersection C plus P A intersection B intersection C. Illustration 11. A card is drawn from a well-shuffled pack of 52 cards. What is the probability of the card being either red or a jack? Solution. The total outcome equals 52 sample points. Let A be the event that the card is red, then A consists of 26 sample points since there are 26 red cards. B denotes the event that the card is a jack. B consists of 4 sample points since the number of jack cards is 4. Hence, ACB consists of 2 sample points since there are 2 red jack cards. PA equals 26 50-seconds, PB equals 4 50-seconds. PA union B equals 2 50-seconds. Hence, PA intersection B equals PA plus PB PA intersection B equals 26 50-seconds plus 4 50-seconds 2 50-seconds equals 28 50-seconds equals 7/13. Illustration 12. A box contains 15 balls numbering from 1 to 15. Find the probability that a ball selected at random is a ball with number that is a multiple of 3 or 5. Solution. Total sample points equals 15. Let A be the event that the ball with number that is a multiple of 3. So, A has 5 sample points, i.e., 3, 6, 9, 12, 15. Let B be the event that the ball with number that is a multiple of 5. So, B has 3 sample points, i.e., 5, 10, 15. Since A and B has 15 as common sample point, ACB has 1 sample point. PA equals 5/15, PB equals 3/15, PA intersection B equals 1/15. Hence, PA union B equals PA plus PB PA intersection B equals 5/15 plus 3/15 1/15 equals 7/15. Illustration 13. The probability that a contractor will get a building contract is 1/5 and the probability of not getting a road contract is 2/3. If the probability of getting at least one contract is 1/4, find out the probability that he will get either of the two contracts. Solution. Let A be the probability of getting a building contract. That is PA equals 1/5. Let B be the probability of getting a road contract. That is PB equals 1/3 equals 2/3. Probability of getting both the contract, A intersection B equals 1/4. PA union B equals PA plus PB PA intersection B equals 1/5 plus 2/3 1/4 equals 37/60. Multiplication theorem of probability. Multiplication theorem of probability can be applied in two situations. They are 1. Multiplication theorem of probability when events are independent and 2. Multiplication theorem of probability when events are dependent. 1. Multiplication theorem of probability when events are independent. If two events, A and B are independent, then the probability that both will occur is equal to the product of the probabilities of these two events. A. That is PA intersection B equals PA x PB. Illustration 14. Two students A and B are independently solving a problem. The probability of A solving the problem is 1/5 and probability of B solving it is 2/3. What is the probability that both of them will solve the problem? Solution. Probability of A solving the problem equals 1/5. Probability of B solving the problem equals 2/3. Probability of A and B solving the problem equals P A and B equals P A x P B equals 1/5 by 2/3 equals 2/15. Illustration 15. A box contains 5 red, 4 black and 3 white balls. What is the probability of getting a white, a black and a red ball? Solution. Total outcome equals 5 plus 4 plus 3 equals 12. Probability of getting a white ball equals 3/12. Probability of getting a black ball equals 4/12. Probability of getting a red ball equals 5/12. Hence, the probability of getting a white, a black and a red ball equals 3/12 by 4/12 by 5/12 equals 5/144. Multiplication theorem of probability when events are dependent. It is otherwise called as conditional probability. Two events are denoted as dependent events when the occurrence or events are denoted as dependent events when the occurrence or non-occurrence of one event in any trial affects the probability of other events in other trial. The probability of occurrence of both the events, when events are dependent, is stated below. P A intersection B equals P A B P B, or P B intersection A equals P B A P A. Since A intersection B equals B intersection A, the important property of these two intersections is P A intersection B equals P A B P B equals P B A. P A. Illustration 16. A bag contains 6 white and 4 red balls. The balls are drawn simultaneously without replacement of the first ball. What is the probability that both balls are of white color? Solution. Total sample points equals 6 plus 4 equals 10. Probability of getting the first white ball PA equals 6/10. Since there is no replacement after the first draw, the probability of getting the second white ball is PBA equals 5/9. Hence, the probability of getting 2 white balls in the 2 draws is PA and B equals PA PBA equals 6/10 by 5/9 equals 1/3. Illustration 17. From a well-shuffled pack of 52 cards, 2 cards are drawn at random. What is the probability that both of them are queen cards? Assume that there is no replacement of the card after the first draw. Solution. Total outcome equals 52, total queen cards equals 4. Hence, probability of getting a queen card in the first draw is PA equals 4/52. Since there is no replacement of the card after the first draw, the probability of getting queen card in the second draw is PBA equals 3/51. Therefore, the probability of getting 2 queen cards PA and B equals PA PBA equals 4/52 by 3/51 equals 3/663. Bayes' theorem, rule for the inverse probability. The calculation of unknown or old probabilities named priori probabilities from the new probabilities is called posterior probabilities or inverse probability. Inverse probability can be calculated through additional information available in the past records. It is one of the important applications of the conditional probability, since conditional probability states that the occurrence of one event is due to the occurrence of a particular event or reason. Inverse probability is derived by a British mathematician named Thomas Bayes in the year 1763. The rules of the theorem are stated as below. Let B be an arbitrary event which can only occur in conjunction with one of the n mutually exclusive and exhaustive events, A1, A2, A3. And, where P be number 0, P be A1, and P A1 I equals 1, 2, n are known. It can be well known after learning of the following illustrations. Illustration 18. 2 persons are competing for a management post in a company. The probabilities that the first and second will win are 0.7 and 0.3 respectively. If the first person wins, the probability of opening a new branch is 0.8 and the corresponding probability is 0.4 if the second person wins. What is the probability that the new branch is opened? Solution. PA1 equals probability of the first person wins equals 0.7. PA2 equals probability of the second person's wins equals 0.3. PB1 equals probability that a new branch is opened. PBA1 equals probability that a new branch is opened if the first person wins equals 0.8. PBA2 equals probability that a new branch is opened if the second person wins equals 0.4. PB equals PA1 intersection B plus PA2 intersection B. equals PA1 PBA1 plus PA2 PBA2 equals 0.7 by 0.8 plus 0.3 by 0.4 equals 0.56 plus 0.12 equals 0.68. Illustration 19. A company manufactures a product, namely X, in two of its factories. The factory I manufactures 75% of the product and factory I manufactures 25% of the product. It is found out that factory I manufactures 70 standard products of X out of 100 products of X and factory 2 manufactures 60 standard products out of 100 products of X. What is the probability that a product X selected at random from factory I is of standard quality? Also calculate the revised probability. Solution. Let PA1 equals the probability of drawing product X from factor I equals 75 100ths equals 0.75. PA2 equals the probability of drawing product X from factory 2 equals 25 100ths equals 0.25. PB equals the probability of getting a standard quality product of X. PBA1 equals the probability of getting a standard quality product from factory I equals 70 100ths equals 0.7. PBA2 equals the probability of getting a standard quality product from factory 2 equals 60 100ths equals 0.6. The probability of getting a standard product of X from these two factories. PB equals PA1 intersection B plus PA2 intersection B equals PA1 PBA1 plus PA2 PBA2 equals 0.75 by 0.7 plus 0.25 by 0.6 equals 0.525 plus 0.15 equals 0.675. The probability of getting a standard product of X from factory I. PB equals PA intersection B equals PA1 PBA1 equals 0.75 by 0.7 equals 0.525. Calculation of posterior revised probability is well stated here. PA1B and PA2B should be calculated, and it is proved that the total of it is 1. Illustration 20. There are 3 persons named K, L and M for a sales manager post in a limited company. Their chance of being selected for the post is in the ratio 6, 4, 3. If K is selected, the probability that he will introduce a new product is 0.5. The corresponding probabilities of the introduction of the new product are 0.7 and 0.4 respectively if L and M are selected. What is the probability that the new product is introduced? Solution. Let the probability that the new product is to be introduced equals PB. PA1 equals 6/13, PA2 equals 4/13, PA3 equals 3/13. PBA1 equals 0.5, PBA2 equals 0.7, PBA3 equals 0.4. PB equals PA1 intersection B plus PA2 intersection B plus PA3 intersection B equals PA1 PBA1 plus PA2 PBA2 plus PA3 PBA3 equals 6/13 by 0.5 plus 4/13 by 0.7 plus 3/13 by 0.4 equals 3/13 plus 2.8 13 plus 1 and 2/13 equals. Computation of expected values. The expected values to be calculated through probability theories are otherwise called as the calculation of mathematical expectation of the random variable. It can be calculated through the following method. Let X as a random variable with possible values x1, x2, x3, xn with corresponding probability p1, p2, p3, pn. Then, the expected value of X can be calculated as through the formula mentioned here. The expected value is also called by means of x, e, x2. It can be calculated as ap1 she2. The concept will be well known through the illustrations. Properties of expected values of the random variable. The following are the important properties derived from the expected values. 1. The expected value of a constant is the constant itself, that is A equals A. 2. A plus bx equals A plus bx, where a and b are constants. 3. When x and y are random variables, then x plus or minus y equals x plus or minus y. 4. When x and y are two independent random variables, then xy equals x, y. Variance of a random variable. The variance of a random variable can be calculated as follows. Let x be a random variable with mean x equals, then the variance is calculated through the equation mentioned here. Variance x equals ex, ex2 ex, x2 equals ex2 ex equals ex2 2. Standard deviation of a random variable. Standard deviation of a random variable is the square root of the variance of the random variable. It can be derived through the same formula used for deriving variance of a random variable. Hence, standard deviation of a random variable is SD. X equals square root of sigma x square minus x square where x equals ex. Illustration 21. Find out the expected values of the random variable, standard deviation and its variance when a die is thrown. Solution. The random variables for the throw of a die are 1, 2, 3, 4, 5, 6. Hence, the probability of occurrence of each value is 1/6. Hence, ex equals 1.16 plus 2. 1/6 plus 3.1, 6 plus 4.1, 6 plus 5.1, 6 plus 6. 1/6 equals 1/6, 1 plus 2 plus 3 plus 4 plus 5 plus 6 equals. Ex equals 7/2. Ex2 equals 1/6, 12 plus 22 plus 32 plus 42 plus 52 plus 62 equals. Variance x equals ex2 equals 2 equals 91/6, 7/2 2. Equals 2.917. Standard deviation equals square root of variance equals square root of 2.917 equals 1.708. Illustration 22. Calculate ex, standard deviation x, and variance x for the probability distribution. Solution. Ex equals P1x1. Since there are 5 outcomes, 3 additions should be done. Calculations are just like the illustration 21. Expected value of x equals 2. Expected value x square equals 5. Here the value of x should be squared. Variance, x equals sigma x square equals 5 to 2 square equals 1. Standard deviation equals square root of 1 equals 1. Illustration 23. Find out the expected random variable of getting head when a coin is tossed 3 times. Solution. When coin is tossed 3 times, the index or power that is raised to the base is 3 since base for occurrence and non-occurrence of event is same. Here it is 1/2. Illustration 24. A game is played by a man with the understanding that he will get 160 rupees for 1 head, 240 rupees for 2 heads and 320 rupees for 3 heads, when 3 coins are tossed at a time. He will not get anything for no head. If the entrance fee for the game is 200 rupees, find out whether he can play the game. Solution. The man will play the game if he will get more than the entrance fees of Rs. 200. When coin is tossed 3 times, the index or power that is raised to the base is 3 since base for occurrence and non-occurrence of event is same. Here it is 1/2. The calculations are as like previous one. Ex equals P1x1 plus P2x2 plus P3x3 plus P4x4. Equals 0 plus 60 90 plus 40 equals Rs. 190. Since the man is expected to get only 190 rupees, which is less than the entrance fee of 200 rupees, he will not play the game. Illustration 25. 2 cards are drawn at random from a pack of 52 cards. What is the probability that it will be I, 2 aces, E, a diamond and a heart, E, a king and jack, and IV, a heart and an ace? Solution. I, total number of cards in the pack equals 52. The number of ways of drawing 2 cards in the pack of 52 cards. NCR equals 5 2C2 equals 1326. When R value is 2 and N value is 52, then 2 number is that of R should be used in the numerator and denominator. That is 52x51 in the numerator and 1x2 in the denominator. Otherwise, multiplications of 1 to 52 in the numerator and 1 to 50 and 1 and 2 of multiplications in the denominator. 50 here means 52 minus 2. The number of ways of drawing 2 aces equals 4C2 equals. Hence, the probability of getting 2 aces. The number of ways a diamond and a heart is drawn. Equals 13C1x13C1 equals 13x13 equals 169 total diamond cards as well as heart card are 13 each. The probability of getting a diamond and a heart is mentioned here. The number of ways a king and a jack are drawn. Equals 4C1x4C1 equals 4x4 equals 16. The probability of getting a king and a jack is mentioned here. IV, the number of ways a heart and an ace are drawn. Equals 13C1x4C1 equals 13x4 equals 52. Exercise for the chapter is well presented here. Please subscribe. MWN.com. Exercise for the chapter is well presented here. Please subscribe. MWN.com.